Hello viewers, welcome to my YouTube channel. My name is NATHANIYELU, Department of Zoology. Today we are going to discuss about nervous system in human beings, that is generation and conduction of nerve impulse. Generation and conduction of nerve impulse that occurs in the neurons. So you can tell neurons are excitable cells because their cell membrane are in polarized state. Here polarized state means axonal membrane inside the axoplasm has negative charge and outside the axoplasm has positive charge. So this differential electrical charges that occurs on the axonal membrane, that's why neuronal membranes are polarized states. Nerve cells exhibit a special property called electrical excitability. So nerve cell exhibit electrical excitability to the external stimuli, so which receive the stimulus, interpret and transmit the stimulus inside as well as outside the axonal membrane. So nerve impulse means a signal that is generated at one place, travels along with the length of the nerve fiber and ends in the release of neurotransmitters. So nerve impulse is a signal that generates and travels along the length of the nerve fiber and its end releases neurotransmitters. When we see neuron, it generates and their ends releases neurotransmitters. Nerve ending releases neurotransmitter. So a signal that generates at one place travels along the neuron or nerve fiber and ends in the release of neurotransmitters. So that we can tell nerve impulse. So on the axonal membrane there are some ion channels. The ion channels which are present on the axonal membrane are mainly leakage channels, voltage gated channels and ligand gated channels. Generally leakage channels, voltage gated channels and ligand gated channels are present on the axonal membrane, which is helpful for the generation and conduction of nerve impulse. When we see leakage channels on the axonal membrane, there are sodium and potassium leakage channels which are present on the axonal membrane. See, sodium and potassium leakage channels present on the axonal membrane, there are more potassium leakage channels are present on the axonal membrane than sodium leakage channels. So there are more potassium leakage channels are present on the axonal membrane than the sodium leakage channels. That's why more potassium permeability that occurs into the axoplasm than sodium. That's why you can tell axonal membrane is more permeable to the potassium and less are impermeable to the sodium. So leakage channels sodium, potassium leakage channels are present. When we compare, potassium leakage channels are more than the sodium leakage channels. Hence, potassium has greater permeability than the sodium when it is in resting condition. Voltage gated channels. Voltage gated channels also, sodium and potassium voltage gated channels are present. When you see on the axonal membrane, sodium voltage gated channels are two types. There are sodium activation voltage gated channel and sodium inactivation voltage gated channel. Same way, potassium activation voltage gated channels are also present on the axonal membrane. So potassium activation gated channels are present. Potassium inactivation gated channels are generally not present on the axonal membrane. Ligand gated channels. Ligand gated channels generally present on the post axonal membrane. Resting membrane potential. So it is the stage that is seen on the axonal membrane when the axonal membrane is not conducting, or when the neuron is not conducting any impulse. That stage we can tell resting stage. Resting stage also contains some potential or electrical charge inside as well as outside, that we can see when neuron is not conducting any impulse, that is called as resting stage. So during resting stage, axonal membrane, during resting stage, axonal membrane is more permeable to the potassium. Axonal membrane is more permeable to the potassium and less permeable or impermeable to sodium ions. Potassium ions are more permeable into the axoplasm than the sodium. So here, during this time, this axonal membrane is impermeable to negatively charged proteins present inside the axonal membrane. Negatively charged proteins present in the axonal membrane is also impermeable during this condition, impermeable to the outside. So that's why inside has more negative charge due to presence of more negatively charged proteins and more negatively charged ions. Same way, outside to the axonal membrane has high concentration of sodium. Sodium concentration is high outside the axonal membrane because sodium is not permeable into the axoplasm. That's why sodium remains outside. That gives positive charge outside the axonal membrane. Inside there are more concentration of potassium. Outside there are more concentration of sodium. So like this we can observe during resting condition. So during resting condition, you can observe separation of electrical charges. Inside, negative charge due to presence of negatively charged proteins. Outside, positive charge. Is present. So this we can tell such separation of positive and negative electrical charges is a form of potential energy. So in a neuron, the resting membrane potential ranges from -40 to -90. Inside during resting condition, it is ranges from -40 millivolts electrical charge, from -40 millivolts to about 90 millivolts during resting condition. So generally it is seen during resting condition, but the typical value is minus 70. Minus 70 millivolts is the typical value that is seen during resting condition. So this minus sign present inside it indicates as negative inside relative to the outside or relative to the extracellular fluid. So at resting phase, axolemma is polarized. That means which can receive action stimulus and it can initiate action potential. If inner side becomes less negative, that means it is less than the 40 millivolts, it is called depolarized. That means inner side is less negative, it leads to depolarization of axonal membrane. If inner side is more negative, it is called hyperpolarized. That means if inside the axonal membrane is above minus 70, that means up to minus 90 millivolts or more than minus 90 millivolts, we call it is hyperpolarization. So like you can observe, it is less negative, depolarization leads to depolarization, this more negative leads to hyperpolarization. During resting phase, activation gates of sodium are closed. When we see during resting condition, sodium inactivation gates are present on the voltage gated channels. So activation gates are closed during resting condition. This is activation gate. During resting condition, activation gates of sodium are closed, but the sodium inactivation gates are open in states. Same way, potassium activation gates also closed. Potassium activation gates also closed during resting condition. So potassium activation gates, sodium activation and inactivation gates. Sodium potassium pump. This sodium potassium pump diffuse ions inwards and outwards and down their concentration gradients through leakage channels. You can see when it is more permeable to sodium due to stimuli and opening of sodium activation gates, sodium is permeable into the axoblast. It leads to depolarization, and after that, when potassium gates are open, potassium leaves out more from the higher concentration to the lower concentration. At this time, it leads to hyperpolarization. That means during opening of potassium gates, more potassium leaves out. That leads to more negative inside. So more negative inside. That means when it inside is more negative, that is hyperpolarization. During this condition, sodium potassium pump play a very important role to maintain resting membrane potential. That's why sodium and potassium ions diffuse inwards and outwards respectively and down their concentration gradients through the leakage channels. Such a movement of ions, if unchecked, They eventually disturb the resting membrane. So during resting membrane, sodium concentration is more outside, potassium concentration is more inside. So through leakage channels, sodium moves inside, potassium moves outside. If it is unchecked, it leads to disturb the membrane potential. Generally, membrane potential minus 40 to minus 90, our typical value is minus 70. If this is unchecked, it leads to disturb the resting membrane potential. That resting membrane potential when disturbed, that causes depolarization. So generally the sodium potassium pump expels 3 sodium, it expels 3 sodium per each 2 potassium ions into it. When 2 potassium ions enter into the cell or into the axoplasm, for every 2 potassium ions, 3 sodium leaves out. For every 3 sodium leaving, after 2 potassium imported into the axoplasm. That means after hyperpolarization, to maintain the resting membrane, it sends out 3 sodium ions from the axoplasm to the outside by importing of every 2 potassium for maintenance of resting membrane. It occurs by utilizing 1 ATP molecule. Utilizing 1 ATP molecule, it import 2 potassium and 3 sodium ions. That's why sodium potassium pump works in the presence of energy. That's why sodium potassium pump works against the concentration gradients in the presence of ATP. That's why active transport occurs. As these pumps remove more positive charges from the axoplasm, then they bring it. That means 3 sodium ions, positive charged ions, expel out. That's why more positive charges are removed from the axoplasm, then they bring it to it. They contribute to the negativity of the resting membrane potential to minus 70 millivolts. Depolarization, it is the rising phase. That means depolarization causes by opening of sodium voltage gated channels. That means when a stimulus applied on the axonal membrane, that means nerve fiber is stimulated, plasma membrane or axonal membrane. Axonal membrane is more permeable to the sodium because sodium gates are open. So when the axonal membrane becomes more permeable to sodium ions because sodium activation gates on the axonal membrane opened by applying a stimulus. So opening of sodium activation gates that allows sodium into the axoplasm. So when we apply a stimulus that causes opening of sodium activation gates, already sodium inactivation gates are open. That's why sodium influx occurs into the axoplasm. Here you can observe nerve fiber is stimulated, axonal membrane becomes more permeable to sodium ions than to potassium ions as activation and inactivation voltage gated sodiums are open. Activation and inactivation voltage gates of sodium are open. That's why sodium enters into the axoplasm. So during this condition, potassium gates are enclosed. Potassium gates are not opened during depolarization. Only sodium gates are open, that causes influx of sodium. Already potassium is more inside the axoplasm. This potassium will not efflux out due to closure of potassium gates. So this results the rate of flow of sodium into the axoplasm exceeds. That means sodium influx occurs through sodium voltage gated channels. Sodium voltage gated channels allow sodium into the axoplasm. That's why axoplasm contains more sodium ions or positive charged ions. That changes the permeability, that changes the electrical charge inside. That's why you can tell axolemma is positively charged inside and negatively charged outside due to influx of sodium at where we applied a stimulus. There we can observe inside positive charge and outside negative charge. So this reversal of electrical charges is called as depolarization. Generally, before depolarization, you can tell polarized state. Polarized state, outside positive, inside negative. Due to opening of sodium gates that causes influx of sodium, that change the polarity inside positive, outside negative. This reversal of electrical charges is called as depolarization. Here we can observe where we applied a stimulus, there we can observe depolarization occurs, that initiate the action potential inside the axoplasm. So it is site A where we applied a stimulus. Adjacent to this we can observe site B. So here adjacent to this site A, here we can see outside is positive and the inside is negative. That means we can tell adjacent to the site of depolarization, that means adjacent to the site A, site B, inside is negative, outside is positive. This changes or this variations in the electrical charges, you can tell depolarization. Of the point which is adjacent to the site of depolarization remains positive charge. Electrical potential difference between these two areas is called as action potential. So electrical potential difference between two sites, that means site A inside positive, inside B inside negative. So this electrical potential difference between these two areas is called as action potential. The particular stimulus which is able to bring the membrane potential to threshold is called threshold stimulus. So we applied a stimulus where in the site A, here in site A we applied a stimulus. That stimulus brings the membrane potential to threshold. That means it brings the membrane to less than minus 40 millivolts. When it brings the potential is at least to minus 55 millivolts from minus 70 millivolts. Generally, resting membrane is minus 70 millivolts. So, if the stimulus brings at least to minus 55 millivolts, the stimulus that brings membrane potential to minus 55 millivolts, that stimulus we can tell threshold stimulus. And the action potential on the membrane when the depolarization reaches certain level is called as threshold potential. See, the action potential occurs response to threshold stimulus. Action potential occurs response to threshold stimulus or suprathreshold stimulus, but does not occur at a subthreshold stimulus. That means stimulus that can brings membrane potential from minus 70 millivolts to minus 55 millivolts or minus 55 millivolts or less. So that type of stimulus you can tell threshold stimulus or suprathreshold stimulus that can initiate action potential. So action potential occurs by threshold stimulus or suprathreshold stimulus. If the stimulus that cannot brings to minus 55 millivolts, that stimulus we can tell subthreshold stimulus. Subthreshold stimulus cannot generate action potential. It means nerve impulse is either conducted totally or not conducted at all. That means nerve impulse, once action potential is generated, that conductor through the axonal membrane, or if action potential not generated. That's why it is called as all or none principle. Due to the rapid influx of sodium ions, the membrane potential shoots rapidly up to plus 45 millivolts. That means once opening of sodium gates, that influx more sodium into the axoplasm, that causes opening of more and more sodium gates on the axonal membrane. When more sodium gates are opened, that more sodium influx into the axoplasm. That's why the membrane potential inside shoots rapidly from minus 70 millivolts to plus 45 millivolts. So it reached to plus 45 millivolts. That's why you can tell it is depolarization, or it is called as spike potential. Plus 45 millivolts is called as spike potential. So after depolarization, rising phase, next comes to repolarization, falling phase. So as the wave of depolarization passes away from the site of origin to the adjacent point, that means we can observe at the site A at site A. Depolarization occurs at the site A. Action potential is generated. This generated action potential moves away from its site to its adjacent site at the center point. So that means inside action potential moves from site A to site B, again from site B to site C. So in this way, the generated action potential conducted from site A to site B to site C like. So that means here during repolarization, the generated action potential moves away from the site of origin to the adjacent point. So here during this stage, activation gates of sodium activation gates are opened. That means we can tell sodium activation gates opened, but sodium inactivation gates are closed. These are sodium inactivation gates. So when sodium inactivation gates are closed, the influx of sodium is checked. That's why you can tell activation gates of sodium remains open, inactivation gates of sodium are closed. Activation gates of potassium also during this time. During depolarization, activation gates of potassium closed. During repolarization, activation gates of potassium are open. Activation gates of potassium are open. Opening of activation gates of potassium that leaves potassium or efflux potassium from the exoplasm to the extracellular fluid. So here we can tell activation gates of potassium opens at the origin of depolarization, that causes potassium leaves out from the exoplasm to the exterior or extracellular fluid. So like we can observe, during repolarization, sodium activation gates are remains opened, but sodium inactivation gates are closed. That causes influx of sodium is checked. During this time, potassium activation gates are opened. That causes efflux of potassium occurs. So that results influx of sodium ions into the exoplasm from the extracellular fluid is checked, but efflux of potassium occurs, which leads to the returning of axonema to the resting stage. That means we can tell axonal membrane at site A. So efflux of potassium occurs by potassium gates or potassium activation gates that causes comeback of electrical charge inside again to the negative. That means again the polarity from plus 45 immediately it come back to minus 70 millivolts. During repolarization, again the membrane polarity come back to minus 70 millivolts. This is called as repolarization. So here, when it reaches to minus 70 millivolts, Generally, sodium activation gets sodium inactivation gets closed. That's why sodium influx not occurs. But when it reaches to minus 70 millivolts, potassium activation gates are not closed. That's why more and more potassium leaves out from the exoplasm to the extracellular space. It reaches, the polarity reaches to more negative. That means it reaches to minus 90 millivolts. That's why it leads to hyperpolarization. So you can observe that. So the repolarization typically goes more negative than the resting potential to about minus 90 millivolts. That means after reaching the membrane potential to minus 70 millivolts resting condition, potassium gates are not closed. That's why more potassium leaves out. That causes more negative inside the exoplasm to about minus 90 millivolts. When it reaches to minus 90 millivolts inside the exoplasm, that called hyperpolarization. This occurs because of the increasing potassium permeability that exists while voltage gates of potassium channels are opened. They closes slowly. Hence potassium voltage gated channels are called as lazy channels. Potassium voltage gated channels are called as lazy channels. That's why it closes slowly when it reaches to hyperpolarization. So now we can observe hyperpolarization reached to minus 90 millivolts. When it reaches to minus 90 millivolts, we call this hyperpolarization. So after hyperpolarization, again the membrane potential will come back to minus 70 millivolts by sodium potassium pump. So here you can observe activation and inactivation gates of sodium remains closed. So during hyperpolarization, sodium activation gates, sodium inactivation gates are completely closed. The membrane potential returns to its original resting state as the potassium channels closed completely. When potassium channels also closed, here sodium channels activation and inactivation channels are closed. Membrane potential come back to resting condition when potassium activation channels also closed. As the voltage falls below the 70 millivolts level of the resting state, it is called as undershoot. That means it is reached to minus 90 millivolts. That's why called it is undershoot. Refractory periods. There are two types of refractory periods we can observe. During this period, even a very strong stimulus cannot initiate second action potential. That means absolute refractory period. During the absolute refractory period, even when we apply a strong stimulus, a very strong stimulus, the membrane cannot initiate second action potential. That is, membrane first action potential is over. Again, when we apply a strong stimulus, the membrane cannot initiate second action potential because it is coincide with the depolarization and repolarization. That means during depolarization reach to plus 45 millivolts, and during repolarization even it again come back to minus 90 millivolts, but minus 70 millivolts, but here potassium gates are not closed. That's why when we apply even a strong stimulus also, it cannot receive and cannot initiate second action potential. That type of period we can tell absolute refractory period. Relative refractory period. During this relative refractory period, the second action potential can be initiated by a larger than a normal stimulus. Even a normal stimulus also can initiate second action potential during a relative refractory period because it is coincide with the hyperpolarization. That means after hyperpolarization, the membrane potential again come back to minus 70 millivolts. That's why it can receive stimulus and it can initiate second action potential. Like that we can observe. When we see here, generally resting membrane potential is minus 70 millivolts. So during this time, when we apply a stimulus that can initiate action potential, that stimulus is called as threshold stimulus. So threshold stimulus can bring the polarity from minus 55 millivolts to minus 70 millivolts to minus 55 millivolts. So it brings, that stimulus brings polarity from minus 70 millivolts to minus 55 millivolts. That stimulus is called as threshold stimulus. So this causes a depolarized membrane that rapidly shoots to plus 45 millivolts. So it rapidly shoots to plus 45 millivolts. So like we can observe during depolarization. After depolarization, falling phase we can observe. That means due to opening of potassium gates, closure of sodium gates, more potassium efflux from the oxoplasm again brings the polarity to minus 70 millivolts. When it brings the polarity membrane potential to minus 70 millivolts, potassium gets not closed, it closes slowly. That's why it reaches more negative. So it goes to about minus 90 millivolts. It goes to about minus 90 millivolts. So that's why here we can observe that minus 90 millivolts is called as hyperpolarization. By active transport, 3 sodium expels out from the oxoplasm, 2 potassium imported into the oxoplasm. That brings again to minus 9, from minus 90 millivolts to minus 70 millivolts. So here it can maintain minus 70 millivolts resting membrane, which receives second action potential. That's why you can tell after depolarization and repolarization, even we apply a strong stimulus that cannot initiate second action potential. After hyperpolarization, even a normal stimulus when we apply on the axon membrane that can initiate second action. Like this, we can observe generation and conduction of nerve impulse.